One of the applications of Gauss's law to charge distribution is finding the electric field due to an infinite line of charge. This is the line of charge that is infinitely long. So meaning all points that are equidistant from the line of charge can feel the same magnitude of electric field. And the charge distribution is distributed uniformly along the line, and the charge distribution has cylindrical symmetry. So we can apply Gauss's law here. In my previous video, I discussed about Gauss's law. So you will recall that Gauss's law, according to Gauss's law, the net flux passing through any closed surface is equivalent to the net charge Q over permittivity of space, and electric flux is equivalent to the electric field times the area element. This is Gauss's law. Now suppose this is the line of charge that is infinitely long, and the best Gaussian surface that we can use to find the electric field at a certain distance from the line of charge is the cylindrical symmetry. This is the line of charge and this is the Gaussian surface. All points on the curve are equidistant from the line of charge, and all points along on the curve part can feel the same magnitude of electric field, and all electric field line that will penetrate on every point of the Gaussian surface are perpendicular to the surface area. So here's the drawing. The electric fields are perpendicular. There's also electric field towards you that is perpendicular to the lateral surface area of the cylinder. Now suppose the Gaussian surface has radius r and length L, and the infinite line has linear charge density lambda. In linear charge density is the charge per unit length. Now if the line of charge has a linear charge density of 10 coulomb per meter, so for the same line of charge, the charge density for 5 meters is still 10 coulomb per meter. Now, so again, the charge density is the net charge per length, or charge per length. So we have the equation of the charge, which is equal to the charge density times the length, and then we can apply Gauss's law. The Gauss's law, the closed integral is equal of the electric field that the area element is equivalent to the net charge per permittivity of space. So since the equation of charge is charge density per length, then we will replace charge by charge density times length, then over permittivity of space, and the total area, which is equivalent to the closed surface, closed integral of the area of the closed surface is equivalent to 2 pi RL, which is the equivalent to the lateral surface area of the cylinder. So we can cancel L. So we have electric field equals the charge density over 2 pi times the radius of the Gaussian surface times permittivity of space. And we know that the Coulomb's constant is 1 over 4 pi permittivity of space. So the permittivity of free space is equivalent to 1 over 4 pi times Coulomb constant. So we will replace the permittivity of free space by 1 over 4 pi k. K again is the Coulomb constant. So the electric field equals the charge density over 2 pi r times, again we will replace the permittivity of free space by 1 over 4 pi k, then that's equivalent to 4 pi k charge density over 2 pi r. So I can cancel pi. So 4 becomes 2 and I can cancel 2. So we have the electric field at a certain distance r from the line of charge is 2 times the Coulomb constant times the charge density over r.